I'm Nancy. I'm a senior statistical consultant at Stat Central. Welcome to our September monthly seminar. We present monthly seminars aimed at substantive researchers on a variety of research design and statistical topics. This month we have Gordana, and she's going to be talking to us about checking your assumptions for regression models, something that everybody should be doing when you're doing your analyses. But we have lots of videos that we have posted of our previous seminars, so I would invite you to check out our website and follow the links to our YouTube channel that has the videos, and also you can download the slides. We also provide statistical consulting for people at the university. So if you're a faculty researcher or an HDR student, you can come to us for some advice on your projects. And we also contract out our services if you have a grant and need help with your statistical analysis. So if you do have some questions about that, get in contact with us and we'll figure out how we might be able to help you. So welcome, Gordana.
Thanks, Nancy. I'll share my screen. Okay, that looks all right. Get rid of this thing on my screen. Okay. I'm going to assume you can all hear me, and if you can't, I guess let me know. Okay. So I could probably teach you for a day or two about checking assumptions, and I've only got 40 minutes. So we're going to focus on one thing. And the thing is going to be residual versus fitted plots. There's lots of other things that you can do to check model assumptions, and we will completely ignore that they exist. But you shouldn't. You should also look at these other things, and there may be other seminars where we do that. So why check assumptions? So every model that you fit, every statistical test that you do, every time you get a p-value of a confidence interval, all of this relies on assumptions. If the assumptions are not met, oh, somebody's got their sound on. If the assumptions are not met, then your p-values are wrong, your confidence intervals are wrong, your science is wrong. So it's really, really important to check assumptions, and it can't be skipped. And I think the reason most people don't, a lot of people don't check their assumptions is because they don't know how to, they don't know that they're supposed to. No one actually told them how to do it. And it's quite, it's a hard thing to teach because it requires you to just do it and try it and see if you can figure out how to learn it. So that's what I'm going to try and do here. So generally, if you have a large violation, that can be easily spotted and corrected. And that's kind of what I'm aiming at in this seminar. If there's kind of little bits that are a bit iffy, that's harder to tell, and you might need a statistician to help you with that. But that's what we're here for. And so I'm not going to talk about tests for assumptions. So there's Shapiro-Wilks and a bunch of tests that you can do for assumptions. Generally speaking, these are terrible. It's much, much better to look at the plots to check assumptions. That I can talk all day also about why these tests are terrible. Okay, so what are some linear model assumptions? So the first and most important assumption is independence. If you don't know what that means, there's a study design seminar on our website you can look at. You can't check this assumption. You have to know from how the data was collected whether or not it's independent. So we're not going to be checking this assumption in the seminar. We absolutely need to know whether your data is independent or not. The second one is linearity. If we're fitting a linear model, which is what we're going to do in this seminar, there needs to be a linear relationship between your response and your predictors. And if there isn't, then you shouldn't fit a linear model. And that's a big assumption, and you need to check that. We can check that on the residual versus fitted plots, which is what we're going to focus on here. And the way you do that is you look for a banana in your residual plot, and if you've got a banana, then it's nonlinear. Okay. Then the other assumption that you can easily check on a residual versus fitted plot is the constant variance assumptions. We have to assume that the variance is constant. And so that we can also check, and we do that with a fan shape. So if there's a fan shape, that means that that's violating your variance assumption. Okay. And there's another assumption, which is normal distribution. We're not going to check that today, but it's also important to check. So we're going to focus on the banana and the fan. That's where we're going to go. How do you actually get a residual plot? It depends what program you use. If you're using R, for example, most of the time when you fit a model, for example, here I fit a linear model with the LM function. If you just plot that model, you don't even need this bit here, but if you plot that model, you'll get, the first plot you get is a residual versus fitted plot. So that's the one we're going to look at. This just tells me plot the first plot and not the others, but that's okay. In SPSS, and it's a little bit of a task to get a residual plot, unfortunately. So because there's all these different menus, I'm not going to tell you how to do it in every menu, but in most menus, there is like a save option. You click on the save and you try and find something that says predicted values. It could be unstandardized, it might not be, and something that says residuals, and then you save those things and they'll show up in your data set once you've run the model, and then you go and you plot them using the plotting menu. So that's how you get residual plots in SPSS. Prism actually gives you quite nice residual plots. Surprising thing about Prism. You just click the little button for residual plots. Okay, so checking assumptions. So every plot in this talk is a residual versus fitted plot. So normally when I introduce these plots, I would like plot the raw data, show a linear model, what that looks like through the data. But I thought because it's a really short seminar, I don't want to confuse you with different kinds of plots. So everything we have here is a residual versus fitted plot. So that's what we're focusing on. Okay, so when I do one of these residual versus fitted plots, what I'm looking for is like something on the left here. And that's kind of just a random mess of points. And in particular, there are a few things that I'm looking for that would show me that I'm violating some of the assumptions. If the relationship is not linear, then we get the banana shape. So we get this sort of U shape, could be upside down. So that will tell you that the relationship between the predictor and the response is not linear. And so that's bad. We don't want that. The other thing we're looking for is that the variance is not constant. And so what that looks like, it's a fan shape. So you see the little fan there, how like these ones are kind of close together and then they fan out as you go towards the right. That's what we're looking for a variance assumption violation. Okay, so neither of these is good. And the one on the left is what we really want. I mean, this is an ideal residual plot. Almost never they look like this good, but this is pretty good. Okay, questions at the moment? Somebody can keep an eye on questions. Any questions, everyone? No. Okay. Sometimes when you have predictors that are categorical, you're not going to get this nice cloud. Even for a good residual plot, you're not going to get a nice cloud. You'll get these vertical lines. That's fine. These vertical lines are good. No problem. What we're looking for here is this fan shape still. So here we've got the fan shape. That's not good. Here we've got the vertical lines. That's fine. That's no problem. We're good with that. Yes, Nancy.
Would it in the fan shaped one, the little cluster is actually in the middle?
Such a good question that I don't have a good answer to. What do you think, Nancy?
Well, I say it's not a fan shape anymore.
No, it's not. But is it good or is it bad? I think it's like, you'll see in a minute, we'll judge residual plots on a scale. I mean, I'm not going to address that exact question, but maybe I'll bring it up again when there's a...
That's right. That's right. Not
Yes.
fan, but
Yes. Oh, so you probably didn't hear that. Nancy, my boss, wants to know what happens. What happens if this little one is in the middle between these two big ones? Like, that's not a fan anymore, but it's still not constant variance. And I guess it's not good, but I think it's not as bad as when you have a fan, because then you definitely have like an increasing thing. Whereas the other one, I'm not sure. You'll get a lot of I'm not sure from me in this. Okay. So then there's one more thing that we're going to look for in residual versus fitted plots, just because we can. So we want to make it the most use we can out of these plots. If you've got to do one plot, you just get what you can. So they're influential points. So it's not an assumption, because I already covered all the assumptions. But what happens is sometimes when a point in your data, or 1 or 2 or 3 points, are in a particular space geometrically, they end up having much more influence on your inference than all the other points. So maybe like a lot of like where the line goes depends only on one point, and we don't want that. We want kind of all the points to inform the relationship pretty evenly. And so we want to look out for influential points. And there are better ways to diagnose influential points. Leverage plot is one of them, but you can spot them often on a residual versus fitted plot. And what you do is you look for on the left and on the right, so on either side of the plot, you look for points that are by themselves or in like small numbers of points. So like, for example, in this plot, you can see this guy is way down here. This is going to be an influential point because it's on the side. So it's not, these guys are not going to be that bad, even though they're kind of like they're like far away from this whole lot, because they're in line with all these other dots. These are not going to make a big deal. But this one, because it's either on the left or on the right, this one's going to be important. So that one's got to be investigated. And we have a whole seminar about outliers that you can have a look at and what to do about outliers.
I was going to ask you, outliers an example of.
It is an example. Yes, so that's what so they generally happen because there are outliers, or because your predictor is skewed and then most of your data is in one spot and not much out here. So that's kind of the 2 times when you usually get these influential points. Okay, any questions from the floor? No. All right.
There are a couple of questions. I assume.
Yes, please.
But one is, how do we know what these issues are?
Yes, I will talk about that. I will talk about correction. Okay, what do they mean? Can you expand a little bit on what you mean by what do these issues mean?
The question is that how do we know what we need to do?
Yes. So we will get to what to do with this information. So the first step is to diagnose. We're going to diagnose the problems. And then at the end, I'll talk about what to do about that with that information. Okay, so we've got influential points. So remember, we're looking for, so we'd like something like this, but this is pretty ideal. Often we don't get that. We're looking for U's or bananas, and for fans, and for, what are they called? Influential points on either side, things that are sort of far away from the others. Okay, so the next bit of our this is going to be interactive. So what I did is I asked a bunch of statisticians, and I think I've got a sample of 6. Most of them are in this room. I asked them this question. I said, look at this residual plot. How happy are you to use this model for inference? So I want to know if you get a residual plot like this, you fit a model, you get a residual plot like this, do you go, okay, we're good, and start looking at your p-values and confidence intervals? Or do you go, no, I'm going to stop here. I need to do something else. I mean, at the moment, you don't know what to do. But yes, so that's going to be the question. I'm going to try to do a poll. So the question is, look at this residual plot. How happy are you? So there's going to be 4 options of happiness. Okay, how happy are you to use this plot, this model for inference? Okay, can you guys, oh no, I haven't. Okay, I'm going to launch. Okay, everyone, please answer the question. It's anonymous. I have 39 people online. I want 39 answers. Can you guys see the results?
Yeah.
You guys can, but can you on there?
No.
Yeah. Okay. That's good. It's interesting. That's good. It's better because it's independent. Okay. 91% participated. Come on. 3 more people. Let's go. Just make a decision. It doesn't matter if you're wrong. Doesn't matter. Okay. I'm going to end the poll. I hope it will display the results. I don't know what happens. Yes, share results. Excellent. Okay. Can you see the results? Oh, wonderful. Okay. So most people are sort of not very happy, would try to hard to find a better model. And I think I agree with that. Okay, so nobody's happy, which is great. I think that's wonderful. Well done, everyone. Okay, so you all just like passed this test with flying colors. I did not know it was going to go this well. Okay, wonderful. Sorry, there was a joke. The joke was, well, this isn't our research. If we'd spent 3 months gathering the data, then we might feel different. Okay, so that's basically what I'm going to go to the next slide and see if we can compare what the statisticians. So the statisticians, the very unhappy is at the top. So we're kind of reversed here, unfortunately. Okay, so this is what the statisticians. Can you guys see online what the statisticians and the poll results? Okay, so the statisticians were very unhappy, mostly, or not very happy. Most of you were not very happy. So the statisticians were slightly less happy than the crowd in here, but of course they've all been doing residual plots for a long time. So the idea is to try and get you to where they are. Okay, so why? So everyone just have a thought about why you think this residual plot was bad. You must have had a reason that it wasn't great. It's the banana, right? It was all U-shaped and banana-like. So if you hadn't plotted this, if you hadn't plotted the residual plot, you would have just gone on with your model and you would have done bad science. But now you've plotted it, you've identified the problem. And in a minute, I'm going to tell you how to fix it, and then everything will be dandy. Okay.
The original plot of the data.
I do. The original plot is like that. Oh, sorry. The original plot of the data. No, I crowdsourced the residual plot, so I don't know what the data are.
Oh.
Okay. So well done, everyone. Brilliant. Okay. So there's like 9 of these.
Laura and I were thinking also the variance.
Yes, you're right. So the other thing is the variance is also increasing. There's a fan shape, but it's a curved fan shape. Yeah. That's true. Both problems that yes, both problematic. So that's good. That's great. Okay, so next one. All right, let's see. So same question. Okay, can I just close this? Polls. Same question back. Okay. Launch. Okay, can you guys see the poll online? You can. All right. Okay, everyone's voted more or less. Okay, oh, still a couple going. Come on, everyone. Let's go, everyone. Let's go. 33, 33, 34, 34, 35. We got more than last time. I'm winning people over. Okay, all right, end poll. Share results. Okay. So, okay, I need to switch to the next one, which is okay, I can't see the results anymore. Oh, this is not good. Oh, here we go. Okay, so most people said they're very happy. Most people here on the call said they're very happy. Actually, the distribution of people on the call and statisticians is very close on this one. So excellent. Basically, you guys are statisticians as far as this question is concerned. Excellent job. Awesome. Okay. Okay. So there's not really many. Yeah. So there's probably like it's not the perfect residual plot. That's why it's what everybody went, but it's like quite good. I would use that one. I'm one of those yeses. Okay. Let's go again. Okay. Back. Launch. Okay. This one. That's a fitted line of some sort that the program automatically gave me.
Oh, okay.
So I don't know.
It's a non-influence.
It does, but yes, the line definitely influences you. I agree. But the line sometimes is there. When you do a residual plot, sometimes it just gives you a line. You have to deal with that. Yeah, that's right. That's right. It'll give you the line. Okay. 2 people still going. Okay. 5, 4, 3, 2, 1. End poll. Share results. Okay. So what have we got? Oh, this is pretty similar again. This is amazing. Okay, so most people and most statisticians are pretty happy, but might try to see if they can find a better model. And so there is one it's pretty much similar. Somebody's not very happy at all. A couple of people are not very happy, but most people are pretty happy. I'm among those pretty happy people. Okay, so what does that mean? Well, we could, but maybe we'll just leave that until the end of the seminar. I did ask the statisticians, and they identified the influential points as the main reason. There were several reasons, but mostly these guys, I think, up here were the problem. I agree, like it's not amazing, but it's good. And so I think that that's what was reflected in the results. So what do you do with them? Well, you find the seminar on influential on outliers that Nancy did not long ago, and you have a look at that. Okay, here we go. And back. We're getting good at these. I mean, we got good at them after the first one. I don't even know why I'm giving you the rest of these. Okay. All right, I'm going to call it and poll. All right, show. Okay, let's go to the next one. Oopsies. This is the statisticians. Were all very unhappy. Almost all of you, or a good 3/4 of you, were very unhappy. Some people were not very happy, would try to find a better model. I think for this one, yeah, I would definitely try to find a better model. That was a very, very extreme fan shape going on there. Very, like, you know, the difference in variance from here to here is like 10-fold. So that's a big difference in variance. And so I would definitely try to find a better model. Or I would definitely use a different model. I don't think I would ever use this model. Okay, again, you can tell me when you get bored of this. There's kind of a range in here, so it'd be nice. It's nice to get through. Okay, so here is another one. What do you think of this one? Another 5 seconds. Okay, end poll. End poll. Okay, so this is what you guys said, which is most people are pretty happy, but might try to see if there can find a better model. Nobody's very unhappy. Let's see what the statisticians said. Pretty much the same. Oh my God, that is a very close distribution. I wish it was the other way around. Yeah, super close. This is like pretty much exactly the same. So yeah, you're as good as statisticians at judging this residual plot. Amazing. Okay. All right. There's questions in the chat. Oh yeah. Okay. People are telling me what. Okay. So what was wrong with it? Yeah. Tell me in the chat what was wrong with it. For those of you who didn't think it was good. Does anyone want to tell me in the chat?
Yeah.
Oh, was it for this one? Still have outliers. Yes. Yes. Agreed. Yeah, there's definitely this guy over here, which is just not good. There's also like some others. There's just a few points that are a bit problematic. This one I think would have the biggest influence. It would pull the regression line a long way. Yeah. Okay, here's one. Let's try this one. Come on, you got 5 seconds. Just decide, just decide. It's okay. It averages out. And ending. Okay, wonderful. Share results. So here are our results. There is a big distribution. Some people are pretty happy. Most people are either pretty happy or not very happy. There are a few on the sort of outskirts. Let's see what the statisticians, quite similar. Statisticians are all in the middle, neither happy nor unhappy. So that's pretty close. Yeah. Okay, so why? Can you share in the chat why you made the decision that you made? Fan shape, one person said. Andrew, anyone else? Any other things? Fan shape, I think I agree. Oh, there's more. Heteroscedastic, also the same as fan shape, true. I thought residuals looked quite random. Can you tell me what you mean by quite random?
Yeah, I thought it was okay. I thought they were just spotted everywhere.
Oh,
so
you thought it was good. Okay.
Normal. Yeah.
Okay, excellent. Cool. Yeah, fair call. So I'm going to stop. I'm just going to go back to the plot without my animations on top of it, just so we can see. So the fan shape that some people saw is, you can see here, like these ones are only about this wide for this whole section. And then here it's a fair bit wider. But it's not like, you know, there was that one when it was like a 10 times difference in the variance. Here it's only like at most a doubling or something of variance. So it's definitely not as extreme as that other one was. But there is a little bit something going on. Sometimes when you get a plot like this, you try another model, it's worse. So then you're kind of stuck with it. So that's why people have said, yeah, I'll try, but I may not find a better model. So yes, I think there's a fan shape, but it's not that bad. Okay, let's do this one. We're almost there. How are we doing for time? Oh, it's still good. A few more minutes. Okay, I'm cutting you off in 5, 4, 3, and done. Share results. Most people are very happy. Few are pretty happy. Somebody's very unhappy. I would love to hear from the person who's very unhappy. So this is almost exactly the distribution of the statisticians once again. Beautiful, really great. But did you click the wrong thing, or do you think, are you very unhappy? Do you want to tell us about it? You don't have to. Okay. You were telling me. Okay, brilliant, excellent. I agree. We're this is a great residual plot. I think this is count data. So I know that's one of those more subtle things, but so there might be better ways to do it, but I think this is great. I would be very happy to use this model. Okay, I think this is the last one. Let's go. Okay, everyone's voted and poll, show results. Nobody's super happy. Most people are not very happy or very unhappy. There was also quite a spread, interestingly, in this one for the statisticians. Most people are pretty happy, so the statisticians are happier than the participants in this. But I was one of the unhappy statisticians, so I'm not sure. So what can we learn from that? There's a lot of variation in how people interpret residual plots. Okay, so I can tell you what I identified in this plot. I didn't even circle anything because it was so rare, so there were so many different answers. I think that this data, there's influential points or a whole set. Basically, it's skewed. Your predictor here is skewed. It starts from 0, and so it's got a lot of observations near 0. Your predictor, not your response. Your predictor has a lot of observations near 0, and then very few out here, and then these are going to be influential points because of that. And so that's what I think the problem is. So I would be reluctant to use this model, but some people would be happy to use this model. So it depends.
In that case, it's probably the model.
But you can transform. That's what I would do. Okay, so oh no, there's another one. We're going to skip that one. Okay, so let's just end with like what to do. So now you know how you're exactly as good as a statistician in identifying problems with a residual plot. So now you just need to know what to do with them. Okay, so we didn't check the independence assumption, but definitely that's an important assumption. So I just wanted to bring it up again. You need to model dependence if it's there. If you don't know what that word means, go have a look or let us know. We'll give you some stuff. There's also a whole seminar about dependence. And then, okay, so in terms of the stuff that we did look at, the variance assumption is what we checked with a van. So if the variance assumption is violated, that's for a number of reasons. So the linear models assume that your outcome is normally distributed with constant variance, but some things are not normally distributed, like counts, for example, are not normally distributed. So maybe you have counts, and maybe so a linear model is not a good thing to do. So you would do a generalized linear model that might be a Poisson distribution or a negative binomial distribution or something like that. So that's a good thing to do if you find that you have a fan shape and you have counts or some other distribution of the data. There are lots of generalized linear models and you can read about them. An easier thing to do, especially if you don't, if the data isn't counts or anything like specific like that, but it's just a bit, there's a fan shape, then you might transform the response. You might do a log transformation of the response, and that often takes care of the fan shape. Basically, anything that starts at 0, anything that can't be less than 0 and is like positive, a log transformation is a good idea, almost always. And so that's always a good thing. That's a good thing to do as well. So that's the response. So the variance assumption is fixed by transforming the response. Sometimes you can do non-parametric stuff as well. I'm not a big fan, but that's another option. Okay, so then what about the linearity assumption? I should have put a banana here. The linearity assumption, banana shape. It doesn't make sense to fit a linear model if the relationship isn't linear. So you need to fit a different model that takes into account non-linearity. You can do that with polynomials. In R, that's just adding a little poly thing inside your linear model. In other places, there are other ways to do that. Or you might do a GAM, generalized additive model, which allows kind of curvy relationships of all kinds. So there's a package for that, for example. Sometimes transforming your predictor also can help with linearity. It depends if it's in the right direction. Sometimes that.
Christina says, orthogonal polynomial or x to the power 2.
Yes, polynomial is like a quadratic or a cubic. So there's like, you can have polynomials to whatever, but often just a quadratic. Like if you just have a U shape, then the quadratic would fit that usually, and then that solves the problem. Sorry?
If you use the poly function in your formula,
Yes, you do. But yes, you do get an orthogonal polynomial, but it's the same as, it can be rewritten. It's okay. I think you can also do raw if you wish. Sorry, there was questions from the statistical audience in the room. I was asking what kind of polynomial poly fits. It fits what's called an orthogonal polynomial, which is a bit more stable than just a normal polynomial. Okay. Sorry. Each other. So the columns of the polynomial, that they're orthogonal to each other. Okay, and then what about if you have influential points? If there are outliers, you need to just go to that seminar. Otherwise, if you have this one where this one just had a skewed predictor, so this predictor was skewed, what I would do here is just log transform the predictor. So not the response, like for the variance, we transform the response, but for this one, we transform the predictor, and then that will generally solve this problem. It might cause other problems like non-linearity, but that's a different problem later on. Okay, I think that's it. All right, questions? I don't know what somebody, Christina said, is an orthogonal polynomial I of x squared? I have no idea. So what happens is like you have ones and then x's, and then the next row is not x squared, but it's just the part of x squared that's orthogonal to 1 and x.
Orthogonal and your
I have a question then. Is it sometimes it can, I find it hard, you can say do a logarithmic transformation and you improve the plots and things, but then you increase the ability to communicate what the model means. Do you have any advice around that one?
Not good advice. The advice I have is to plot the output of your models. So there's packages like SJplot and EMmeans, which can plot like the relationships that you're modeling. And that can be a good way to communicate. Yeah, it's harder to do. Obviously, if you have a linear model, you can say when I increase X by 1, Y increases by whatever, and that's really convenient, but it's just not reflecting the relationship that you're modeling. So there's not much you can do about that. But yeah, plots can be really good with confidence intervals and stuff. Anyone else? Yeah.
If you have several explanatory variables and you want to fit a linear model to check linearity, to check them one by one, then you could have this plot, right?
Yeah.
Two variables, then your residual would be equivalent.
Yes. So the question was, if you have more than one predictor variable, should you be checking the linearity of each one against your response? technically you should be checking what's called partial residual plots. So it's not a plot of the predictor against the residuals. It's like the residuals are from a model basically excluding that predictor and then comparing that to the predictor. And that tells you if like the addition of that variable is linear, which is what you really want to know. So no one ever does it. But yes, it is possible to do. I think most people will just plot one residual versus fitted plot and be done with it, unless they're worried about something.
What on the x-axis? Or quickly again.
It is the fitted, no, it's the predictor, raw predictor against the residual of the model excluding it or something like that. There's actually a couple of different ways to do it. I think that's one of the ways. Yeah. Okay. So okay, Nancy, all right, that was Nancy. Should you identify outliers before transformation or after or both? I think, and Nancy's a better person. What do you reckon? I don't remember about outliers.
I think that I would be concerned about outliers after I was happy with.
Yeah, I tend not to look for outliers. Well, like I might like data cleaning. In the data cleaning steps, I might look for, very unusual observations that I might want to check out. But then I'm more worried about them if they're influential. If they're not influential, it doesn't really matter that they're outliers. Any more questions? Okay. Well, thank you everyone for coming. I hope that was useful. Let us know if we can help you with your residual plots. Yes. Yeah. If you just Google Stat Central seminar, you will find them.